So good morning, everyone. My name is Sindhusha, and I'm a software engineer at ASML. I have experience writing software for embedded applications for the last 8 years, and some of them have been a wide range of applications like safety critical ones like avionics software, medical software, and now at ASML I write software for photolithography machines. And in this presentation, I kind of want to go over some of the challenges we face while migrating to C++ from C, because majority of the languages that we use currently in embedded applications is still C, and kind of present over some challenges. And this is going to be a generic presentation. I would love to see if you can have any kind of input on how you think C++ can be useful. So let's jump in. Before I do get into like the embedded aspect of it, I kind of want to talk about what exactly I do at ASML. A lot of people do not understand what ASML does, but you'd be surprised to know that we're kind of well connected to the modern world as it is. Chips are everywhere. They might be small, but their impact are tremendous, right from like your laptops, your phones, your wearable technologies, your entertainment. Cars, chip shortages causes car shortages, medical devices use them, and then obviously as and when we keep moving to cloud and artificial intelligence, we also need more and more high-powered, high-processing chips. So today, Moore's law drives megatrends that shape our connected world. We are moving to cloud, we're using 5G technology, artificial intelligence, IoT, we're using a lot of high-def gaming, simulation, AR, VR. So you can see that there's like a great demand for really high-powered chips that we can get. So a few decades ago, chips were just to provide processing for PC. We had 1 million PC developers, then we went into the mobile and cloud era. We went to 10 million mobile and cloud developers and PC developers. More processing speeds, more processing capacities, more controllers options, more language options. And so now that we're in the intelligence era, we have more of AI related demands. We have more high processing mobile and cloud demands. And then obviously our PC also has been improving. So we definitely need more high powered chips. So that's where ASML comes into picture. We'd like to introduce ourselves as a relatively obscure Dutch company, but we kind of are the mega players in the chip manufacturing industry. So what do we do? So all of us know what a Moore's law is. You probably have come across it in some computer class at some point. At one point, your wafers, which contain the transistors, were the size of your fingernail, and now we can fit like billions of transistors within that small area. So clearly, our processing has been increasing. So that's where lithography comes into picture. We know that we want to have transistors, billions of transistors within a small area. But the best way to do that is to use photolithography. We use lasers to be able to etch the metallurgical surface, and then once the wafer is processed, it's ready for like the next part of the lithography and process of like marketing the ICs. So that's where ASML comes into picture. We provide the photolithography machines that are in use today. Our major chip makers are our customers, all major chip makers. We have TSMC, Samsung, Intel, Micron, Texas Instruments, etc. So if you have a device that uses any of these chips that are manufactured in these places, we probably are the ones providing the machine for them to do it. So now, I'm not going to go into details over how a lithography system works. Although the title is a little misleading, my goal to show this was just to show how complex the system is. This is sometimes the size of 2 of these rooms, and you have a lot of hardware components all in it, and you have software controlling the hardware, and it's using laser. That purple light that you see over there is laser technology. And then you see a lot of things moving in minute details over here. And then over here, this would be the wafer where the laser etches onto the wafer. And then you have this over here would be the reticle. Sorry, Johan.
Is that an EUV machine?
I'm not entirely sure. I think so. Is it? Yeah. So that would be the latest, probably. I'm so, yeah. Extra. Yeah. So then we have the reticles, which would contain the pattern that we want to etch onto the wafer. So both of them are kind of moving in alignment. So there's a lot of precision involved. And when you're writing software, you have to keep in mind the immediate effects of it on a physical level. So that is why I want to now segue into understanding what embedded systems are. This is going to be, again, a little bit generic. I don't know what experience you guys have in developing embedded systems, so I'm just going to go over some of the characteristics. The first thing is real-time operation. All of your embedded systems always are like interacting with the real world. You're interacting with your sensors all the time, your transducers, actuators, and then they process that data and they have to interact into that same environment. Then you have your tight design constraints. Even in a sophisticated network like the, sophisticated machine like the lithography machine, we still have components which have some tight design constraints like speed. We have memory constraints. We have the size constraints. So we have to work through all of those. Then you have single functionality. Although I don't think single functionality would be the right way to say it, it would probably be more limited functionality. So when you design and develop an embedded systems, there is almost a singular purpose to it, and you can't keep adding on more and more functionality. You want to keep it to a single or focused functionality. Then you have time specific, so that means it needs to be able to interact within a set time frame. It can't take forever to process and then forever to, let's say, move the reticle wherever it wants to. Then we have high runtime reliability. More than the average PC, we want your embedded systems to be definitely reliable in the field. We cannot, compared to an average PC, you probably would require a higher percentage of runtime reliability. Then you have fault tolerance. Whenever an embedded system runs into fault, we cannot afford having the system completely crash down. And even if it does, it should be able to recover immediately. So in cases of like safety critical systems, we cannot have faults in like an airplane, because something like that would cause the airplane to crash. You want to be able to have the system to recover. If one of the component that you went into one of the fly-by-wire of airplanes crashes, then the entire airplane sometimes could be affected. Then you also have, like in lithography machines, although it's not safety critical, there's a financial element involved. For a system as big as that, in order to recover from the basic initialization phase would take hours, and that costs a lot of money. And customers are not happy when they have to spend extra time or they lose time for things like running into faults and the system not able to recover because they're spending billions for this machine. Next is built-in diagnostics. Most of these embedded systems, obviously, you're not going to be in there in the field debugging them. You have to be able to have a built-in diagnostic system that can help you debug and then kind of recover the system. Limited user configurability. It's really not like a mix and match kind of a system. You can't install whatever software you want. You can't choose. There's some amount of configurability that you can do, but that is also very limited when compared to like a PC or a iPad. Longer time to market. Now, whenever we do ship our products in embedded systems, we always have a lot of higher qualification guidelines. We do thorough testing, and only then we ship it. So it's an entire process starting from the hardware design, the software design, the testing, qualification, and then we ship it. So there's a lot more time and effort involved in marketing your product. Concurrency, again, kind of like any other embedded systems, safety critical or photolithography, you always have to keep in mind what information you're getting, and you have to make sure that you're always dealing with that information in a timely manner. So you always have to work on things at the same time. Scalability, again, this is kind of dependent on how powerful your microprocessor is that you're using for your embedded systems. If it has a certain limit of hardware input-output, what's the right word to say, like input outputs that it can do, then in that case, that is the limit to it. And security, you're also working with a lot of real-time data, let's say GPS or I don't know, any other like network data. You want to make sure that your data integrity stays accurate, and whatever data you're using and processing is not corrupted. So another use case would be like if a system does crash and you have to restart itself. Sometimes embedded systems are known to be able to do that from reading from the ROM and then pick up where they left off. And that again requires data integrity. So again, understanding embedded systems depending on your performance and functional requirements. You have real-time, standalone, network, and mobile. Pretty generic. Based on capacity of the microcontroller, you have small scale, medium scale, maybe robots, sophisticated, which is more like photolithography machines. And then to understand the layers that go into embedded systems, you have the hardware layer. You have the drivers and the board support that directly interact with the hardware layer, the hardware abstraction layer. And then you have the real-time operating systems, which provide the kind of a small version of an operating system, usually Linux, for use within your embedded environment. You have your application programming interface and then application code. In a lot of cases, yeah.
Oh, I was just curious. You mentioned Linux. I thought I had heard previously that Linux was not considered to be a real-time OS. Is this like a fork of it, or is that just
it's kind of like it's based off of Linux. It's not Linux itself,
Okay.
but there are like it's very similar to a Linux-based.
Okay.
It's a Linux-based kernel.
Mm-hmm.
Then you have application code, which usually is like more lenient with what kind of application you write, and probably the best use case for your C++ if you want to. So now we understand what embedded systems are, we understand their characteristics, and now we can go into their constraints. Number one, we have low power consumption. So if you want to write code, even with C++, we have to make sure that the code is very efficient. We can't have unnecessary processing because that does involve power consumption. You have smaller code size because we're working with limited memory. We don't want to cause bloated code, but then again, that's again a little bit of trade-off. If you especially have the ability to work with a slightly bigger memory, it's okay to switch to an object-oriented programming just because it can help you maintain the code base and kind of have more ease of design, ease of development. Real-time performance, again, working with hardware on a regular basis, and then quick responses to critical situations. We don't want to hang for like hours on end, have to restart the system altogether. And for certain hard real-time embedded systems, you have obviously time-bound operational requirements. So again, whatever code you write, you have to make sure that it doesn't get hung in between, and you have to make sure that there's like a good error path leading you back to a workable system. No, don't want to go into much of detail on this. It's just to kind of peruse whenever I upload the slides. And based on execution time, our constraints are clock frequency of the microcontroller we're using or processor, bit architecture, and too many floating point calculations can slow it down. Again, this is depending on what processor we use and the memory that we're working with. Code size, and then we have for power consumption, the number of calculation, number of calls, your call stack, clock frequency, and then and we also have like the reliability on maximum number of inputs, maximum number of, or flexibility on maximum number of outputs is also very limited, and overall security of the system. We don't want to be able to have like someone be able to hack a hardware, not hardware, a real or embedded systems that has that could potentially affect the security of people, like again, safety critical, or even photolithography. You don't want to be able to have an option for hacking. So there's a demand for predictability. That is one of the main things that you kind of have to keep in mind at the forefront when you're developing code. We want to know that every path that we take is predictable, and sometimes we do end up having to fight for the millisecond or the microsecond. So overall, I've gone over all of this, and for the last few decades, C has been the predominant choice for majority of embedded applications, and some of this is because the industry that embedded applications fall under are heavily regulated. In order to write code for avionics, it can either be C or Ada, because that's the only qualifiable language that they have, because they don't trust C++ for some reason. And I think it's probably just because you don't have as much people doing research in an embedded application or an embedded environment for C++. You also, I think, in medical devices too, is the same issue. Slowly, at least in ASML, we have a few components that we can start using C++ for, and we're even at a lower level, we're starting to migrate to C++. And we see a huge change in the way we develop code, change in our architecture, but it's going to take some time for us to catch up to it. But this is a general trend that we see. It's still predominantly C, and kind of just to go over the innovation distribution curve, obviously, we probably don't come under innovators, but maybe early adopters, and slowly, hopefully, everyone will move towards the early majority or a late majority, but please don't be the laggards over there. So now, going into some features of C++ that I think are really neat in an embedded context. Obviously, function overloading. I believe I bring up these points because a lot of embedded developers tend to believe that these are enough reasons to not go to C++. So I think the C++ community at some point did do a research into this, and they did find that some of these have very minimal impact on the code base. But then again, you have to be extremely careful about how you use C++ and use good coding skills for that. So function overloading has been shown to have zero impact on the code. Use of context expression obviously is helpful for using compiler optimizations. Better casting rules, definitely better than what C uses, just because you have a wide range of it and it's more explicit. You have pass by reference. You can do this in C too, but in general, pass by reference in C++ is just generally safer. And you don't have to worry about allocating memory. You don't have to worry about initializing it before passing it and stuff. Better memory management, especially when you have to deal with direct memory access or anything that has to do with locking the memory and stuff. You have something like a scope-based resource management that kind of allows you to kind of keep your locks and you kind of avoid memory leaks, because many people forget to use the free function in C, and I'm sometimes one of them. And then it's obviously the scope-based resource management. A lot of cases we've had to directly use memory, so mutexes are definitely really good. And then you have templates, which kind of reduce repetition and dead code. This is a bit of a double-edged sword. You have to keep in mind that we're working with somewhat limited memory, so overusing templates if you don't need it as much can clog up your memory. And namespace are definitely a lifesaver, because C uses prefixes in order to work around, and it's not really that, it's not neat, it's not clever, it just is, that's it. Features that can be challenging. It's not exactly challenging, I would say, but there's some things you have to keep in mind. Anything that's related to memory in some way, whatever you write, you always have to keep in mind what are the speed implications of it, what are the memory implications of what you're writing. So the runtime type information, if you have to use like a runtime related to obtain like the type information, it's really not efficient, and we really don't want to do that. in an embedded context. We want to keep it as static as possible. Use templates with care. Again, like I said, it can lead to extra memory usage, so we have to keep that in mind. I'm not saying it's not bad. I still like them. It's just we have to keep in mind about the memory footprint.
I just want to make a comment. We do a lot of template metaprogramming on our firmware, and we have templates that are like their type name is literally kilobytes in size, and those don't use any memory at all because it's the type system that we're using.
Oh, okay.
And then we have other templates where we weren't very careful with the storage allocation and how they're being used, and they use many, many, many kilobytes when really we should have used an array or something else so that we're not like duplicating the assembly code. When we expand the template.
And are you working with a limited memory at all in your firmware?
Yeah, like 64 kilobytes of data memory at the moment.
Okay. Use of dynamic memory, obviously, we as embedded developers are not big fans of dynamic memory usage, but if it's needed, always keep it to the minimum. We do not want to run out of memory during runtime. So again, better C++ coding skills is definitely needed if you want to use it for embedded systems. Keep in mind, exception handling is amazing, but you always have to, just like in application level, but maybe a little bit more for embedded, just because you want to know there's a real world effect on it, which is you want to make sure that error path that you take is deterministic, and you know where it's headed and how you can test it, because in order to qualify your embedded software, you do need to be able to show that you've tested all paths of your code. Writing to ROM is again essential, so again keep in mind that you have to do that input-output operations on a regular basis. So there are some case studies. Yeah.
Sorry, what do you mean by writing to ROM?
Well, don't necessarily mean ROM, but more like in some of my applications, I've had to take the status of the machine and write the status onto the ROM on a regular basis. So that if the system crashes, I'm not starting from the basic. I can pick up where it is, because it would take time to reach that stage again. So it's just time consuming to start an embedded system from the scratch. So we want to be able to kind of have a backup of things. So, and that being said, you don't have to keep a backup of like years long data. Depending on your use case, you can do it within the last like 24 hours or 48 hours, maybe 1 week, and then just use that data and rewrite that data. So that's usually the use cases I've seen. Some ASML case studies where, like in the department, we've till now used just C, and so we're slowly starting to move to C++. And I'm not going to go into too much detail of this because I really cannot show you much of code, but I will try to talk about some of the things that we learned along the way.
Good question. So when you do the embedded program design, do you use specific compiler or just use a generic compiler?
Specific? Normally?
Normal, like GCC.
I've used GCC in some of my work that I've done. I've never written too much of driver code. I've mostly stuck to the application level to some extent. Maybe towards the driver code, depending on the controller, you might have to, but those are very like niche controllers that don't usually have like, they're like smaller projects that don't really have as much impact, I feel like. So yeah, looking at embedded systems, you have application software, and this is in our case, we had the application software that we were trying to move to C++, and then we had your the layers of process control. Then you have your actuators, which are being like sending information to the process control, and then your actual physical network layer. So earlier, we had our mechanical engineers develop all these models in the Simulink, and then as software engineers, we would write interfaces. We'd first understand what the models are doing, what the behavior of it in Simulink is, and try to understand what interfaces we have with process control, and then try to put it all together. It was very manual connections between all of them. was harder to maintain. It was more time to develop because people have to come up to speed to it if you're new to it, and then more complex because you're working with mechanical engineers on a regular basis, and they don't understand your software, but you need to understand their functional side before you can write that software to be able to control the hardware. So that collaboration was a bit difficult. You needed to understand network interfaces because all of these devices were like on networks, data types, and then what available interfaces I could use. Next, our new way of working is mechanical engineers do their thing. They develop it on Simulink, and we just use the Simulink models to generate our C++ classes. And although it can also develop C code, C++ generated code has been a lot more useful because we're still using the same terminology that the mechanical engineers are using because the C++ code matches the functional blocks that they are using, and it's a lot easier to develop from there on. So lesser lines of code, it's easier to maintain, it improves type safety, and facilitates collaboration. So I don't know if, you really don't need to see about the details of what that code is, but I wanted to show the size of both of them. On the traditional C side, we're doing everything manually because we don't have like a set generated code that we could use. And this was to like check the range collision for one of our components to avoid collision for a reticle. And then the C++ code from the generated Simulink classes that we could use was just a line. Now, this is definitely easy to maintain, definitely easy to develop. Whether or not this is very efficient, I do not know. I don't know how much space this is taking because at the moment I don't have access to this code, so I really could not run any of the call stack to look at it, but ideally I wouldn't be surprised if C++ does take a little bit more, but it's again a trade-off, so you have to keep that in mind.
It's incorrect.
Is it?
Basically, C++ compilers do a better job in optimizing out your code. So even if you see something that looks like that, in the end of the day, your code will be small. Most of the time. That's what I feel.
So this particular case, I had a conversation with the engineer who actually developed this, and she was talking about possible implications of it and said that there is a possibility that it could be higher. I don't have the metrics for it, so it's...
So it would be interesting to see.
It's not completely true because it really depends on the use case. I think you kind of...
I agree with that.
Wait, I just want to, as a background as embedded developer, I agree with you that, some cases embedded developers are, intimidated by C++ for no good reason, but it's not, you can't say that as a, so, yeah.
Yeah,
You're right.
keep in mind, we're using a pretty old compiler as well.
Yeah, we're using a very old one too. So. Yeah.
But you need to benchmark, you need to test it.
Yeah, we need to do all that. Yeah. So that's the reason I'm not sure about the implications of this. In some case, even if it was a little bit higher, I don't see it being a huge problem, just because overall, in sophisticated devices like this, we do have a little bit of memory leeway that we can use. So that's what I would think. But I'm willing to go back to my engineer and ask her metrics of it. So our next case study would be more of like changing from our monolithic architecture that we used, because earlier they had the component had starting from, we did step 1, step 2, step 3, step 4, and then one after the other. Finally, we finish our alignment. And this was, again, harder to maintain. So they wanted to do something that was more configurable with rapid prototyping, reduce patch overlaps, and then we could develop all at the same time instead of having one feature after the other. That is usually the case when you have to develop like monolithics at times, and modularity and ease of testing. So what they did was they took an entire action sequence that they needed to do, which was, okay, we need to do, once this step 1 starts, then we do step 2, step 3, and then instead of doing one after the other, in some cases they parallelized it, and they created what was called like a pipe, which is basically the lowest level of like operation that you could get, which is, again, this is all developed in C++, and so all of these pipes are derived from a base class that defines what functions that you can use, and then all of them can be pretty much run parallel. Yeah, so we're moving from monolithic. It's hard to maintain. Don't need to go over that. Everyone knows that. And then command and strategy is like as soon as we get some thing that needs to be processed, we have a particular strategy, we push it off to the proper pipe, and then we let that take care of it. Yeah.
One thing I was kind of wondering, and it says parallel execution up there, so that might be my answer. I was just wondering, like typically in your use cases, like do you find that you're often writing threaded code, or is the answer that like it's not worth it, we need the predictability? Like I'm just kind of wondering, like, is it common to be writing threaded code for embedded applications, or is it usually just serial?
It depends on, again, the use case. Some of your embedded systems I've seen have used just one single thread, but again, for slightly complex, more calculations and stuff, I do feel like multi-threaded would be a good approach, and I have seen that being used. But yeah, so this one specifically is, again, parallel, so yeah.
Even if you don't have threads, there's interrupts.
Oh yeah, that's true, yeah.
Can I add something there, like probably like working on the EUV source, like with probably the place where we use C++ the most with respect to the scanner that is mostly C focused. And we actively try to avoid threats in the embedded. Like,
What I was thinking, there would be use cases where it's like we need the predictability, like we just want single thread.
Yeah. Mostly like to my mind, I don't know, Lionel, if you have any idea, but I don't recall threaded code in there. I mean, it's multi-task is on real-time OS, so we have tasks, but it's not.
Yeah,
Synchronization is just done.
we even had cases where we actually add, low-level drivers implemented using threads, and we put them out. We refactor them to use single thread.
And another common part in eventually sometimes because it's more, like you can define the boundaries of whatever, it's only 2 threads.
Right.
But yeah, it's interesting stuff.
Okay. All right, so just a quick check on the time. So in conclusion, there are some bottlenecks that's keeping us from using C++ in embedded development. First this is something that Herb brought up yesterday, gap of workforce knowledge. Most of our embedded developers are people from somewhat of an electrical background. They're used to thinking in procedural view, and it's hard for them to adapt and a more of a like object-oriented design, trying to understand, tinker around with object-oriented. They want to stick to their comfort zone. It's understandable, but then again, I feel like if we can have more people pushing towards it, that early majority, if we can reach that, we can have more people using it, and it just makes our life easier overall. And that's one of the concerns. Another one is some of the designs that I've worked with are heavily monolithic. They've been designed some 30 years ago. It's legacy code that you sometimes have to work with in order to, even if you have to add new features, you're pretty much adding to legacy code. So you're trying to maintain some level of like uniformity that causes a little bit of delays if we want to use something new. Gatekeeping tools. Again, this is something I've seen in aviation again, especially, or sometimes in companies. I don't think ASML deals with this, but if a company has a specific tool that they've used over the years, they're really not willing to accept a new one, and it kind of slows us down. And then adapting C++ in legacy code is definitely a challenge. Again, something that Herb said yesterday, which is we could probably add our new features that we're adding in C++, and that's what we're doing. In the last 2 case studies that I had, we've been a heavily C department, and we're slowly starting to develop C++, and there's a learning curve there, but we see the advantage and we're liking it so far. So the only challenge is how do we get our old code to slowly move, but we'll get to there. And if you guys have any suggestions, do please let me know. So I'm going to leave at that. I would love you guys to join the ASML software community whenever you can. It's a great place to learn and yeah, get inspired, be inspiring. So that's all I have. Any questions that I can take?
That's a great talk. Really
No,
enjoyed
thank
it.
you. This is my first time, so I am
cool.
happy about it.
Cool. Do you guys, so you mentioned this ASML software community, and you guys are moving to C++. Do you have any, like, are you thinking about or having any plans for open sourcing any of your libraries or components?
That's a good question. I do not know if you guys.
We do have our open source internal community.
Uh-huh.
We are not really allowed to open source from external, but internally we have our own photography and we are working on it. There are specific things, not in the US, but in Europe, working with other programming languages that they are able to have their work in public, but not as a manager.
Okay. Another question. Do you guys use open source libraries in your software?
Yeah.
Very, very, very.
Is it due to like license constraints or?
Due to that, it's also, there are many reasons, but yeah, the liability of using open source, I think, for is an issue.
Yeah, but there is a path.
But there is a path, yeah.
And like basically they need to be vouched in terms of licenses. And if you want to use an open source library, you can without requesting and see. It's like limit.
The thing that yesterday evening we talked about how long it takes to get a new language to be introduced in some takes a decade. In our industry, once the language has been adopted, it takes another decade for us to actually end up using it, right? So open source is has been around for quite a while, but for us it's still not something that is necessarily something that we will use right off the bat, right? It requires a lot of thinking before we actually do that.
So then do you use the C++ standard library that comes with the compiler?
Yeah.
Is that Clang or GCC or both?
GCC.
One other thing I was curious about, I'm sure testing for these systems a lot of the time is very challenging. I was just wondering, I think some of the other talks have talked about like fuzz testing and stuff like that, where you kind of like randomly profile guided, but you generate random inputs for like the test. Do you guys use any kind of fuzz testing, or do you see a place for that in embedded development?
I think I do see it. I don't think ASML specifically uses that. We do more of unit testing, and then we do physical testing, and we also have like auto testers and stuff that constantly check the functionality. But I do believe in one of the projects that I worked in a previous company, we did have something similar to it, because we had to check. It was again avionics software, so we had to check every robustness in inputs and outputs to ensure before we can qualify the software. Again, it's based on at least in avionics, it's based on the class of the software. But yeah. It would be nice if we could do that, though. It's always good to have extra testing.
One thing we started to do that might interest you is that we recently switched to use the C++ core guidelines for basically guidelines for how to use C++ and so on. And we use a checker that basically implements all the rules that the C++ guidelines have defined. And we try to enforce all that stuff. And one of the things we find is that we have to limit the usage of C++ to avoid engineers making mistakes. If you open the door,
Actually, the problem that we have is the opposite. I've looked at AutoSAR and Misra C++ guidelines. They're kind of awful. They're very frustrating in some of the limitations. And we try to use Clockwork and Coverity. Our code base is C++ 17, and those tools cannot parse our code base, which is valid C++ 17. It does not comprehend.
Actually been updated to 17 just recently.
Misa's being updated, yeah. Is that based off of the AutoSAR?
I am.
Part of it.
Okay.
It's almost
Either way,
with the margin, but that's why I think they're so restricted.
I mean, this is, they wanna verify as much as possible. It's
Yeah,
part
that's
of
what I
the-
mean. Like,
Yeah.
for example, in our case, like the market is not regulated, so we still have a customer demand of running this machine 24/7, right? So
Yeah,
we
yeah.
need to make sure that our system is as reliable and
Oh yeah,
as
I agree.
as possible.
So my firmware runs in our chipset, and the only time it turns off is when you physically take the power or take the battery out of your laptop, right? So it's always running. And if we get into some kind of crash scenario, we do a hard reboot of your system.
Cold
Yeah, and you don't even get like the Microsoft crash screen, so we can't blame Windows, right? People know like, oh, the hardware's messed up somehow.
They don't know anything because it's a black screen.
Yeah. The kind of rules in AutoStar that really turn me off is like, don't use friend functions because it breaks encapsulation. I'm like,
Yeah.
that's crazy. Of course, it actually helps with your encapsulation in many cases to use the friend functions. And so, I would end up finding, reasons for just about every single one of those rules why we actually want to use that feature and why it's actually more safe and we can prove more things at compile time, that it's correct and we're not going to have issues, right?
So basically, what you're saying, you're combining Mithra with core guidelines, and
We don't
just
know. We
changing
don't use it.
coverity for that. Or
No, we don't even use it. Coverity and Clockwork basically,
But-
they
but-
can't work on our code base, and I don't want to cater to those tools that are basically have a broken implementation of C++ 17,
Mhm.
and then we're moving to C++ 20, right? Which I have very little expectation that these tools are going to be able to comprehend that, as well as the compilers do.
Well, Coverity does a pretty good job. I worked at Medical, so we used Coverity with C++ 17, and it did a good job, but we used Mithra, and we combined it with core guidelines.
I think for many, many, many code bases, they're excellent tools. But with the number of GCC and Clang ICEs that I'm getting, like internal compiler errors, even just that is hard for the compiler sometimes. And I don't really want to work around two more tools.
I think my
I'm sorry.
No, it's a good conversation, though.
I'm so sorry.
It's a good
We're really
conversation.
excited about your
Yeah.
talk.
All right, any other questions? We are a little over time, I think.
Right at time.
Oh, we are? Okay, great.
Thank
Yeah, thank you.